Imagine you run a service with 1 billion registered users. The moment someone types a username and hits sign in, your system has to answer one simple question. Have we ever seen this person before? The obvious approach is to keep the full list of users in memory and scan it on every login. But 1 billion names is an enormous amount of RAM, and scanning it on every request is painfully slow. What we actually need is a small, fast pre-check. A quick test that can confidently say, this username is definitely not in our set, so don't even bother hitting the database. Enter the Bloom filter. It's a probabilistic data structure for exactly this job. It does not store the items themselves. Instead, it keeps a single row of bits, and at the very start, every single bit is 0. To add an item, we run it through a few independent hash functions. Each hash function spits out an index into our bit row, and at each of those positions, we flip the bit to 1. So adding one item lights up several bits across the row. Add a second item, and it lights up its own set of bits. We never store the original strings at all, just these flipped bits. Now the membership check. Someone asks, is the username Alan already in our set? We hash Alan the exact same way and read the bits at those same positions. If even one of those bits is still 0, then Alan was definitely never added, because adding him would have set it. This is the key guarantee. A Bloom filter never produces a false negative. But if all the bits we check are 1, we say, probably yes, Alan is in the set. And in practice, most of the time we are right. Sometimes, though, we are wrong. A brand new username, one we never added, happens to hash to bits that other, unrelated items have already lit up. Every bit it points to is already 1. So the filter confidently says yes, but Alan was never added. That collision is called a false positive. Why does this happen? Because bits are shared between items. As more items get packed into a fixed array, collisions stop being rare and become inevitable. But here is the trade we are making. We give up perfect accuracy on the yes answers, and in exchange, we get something genuinely remarkable. A Bloom filter uses only a tiny fraction of the memory the full list would need. It answers in constant time, no matter how many items you've added, and it never misses an item that is truly there. And you are in control of the error rate. Give it more bits or more hash functions and the false positive rate drops. You choose exactly how much accuracy you are willing to pay for. That is why databases, web browsers, and content delivery networks all use Bloom filters as a cheap first line of defense before doing the expensive lookup. Maybe yes, definitely no. A tiny amount of memory and never a false negative. That is the Bloom filter.